Welcome to the deep dive. Today we're really getting into something fascinating. The advances in image recognition, specifically looking at deep residual networks, ROVNets.
That's right. And we're grounding this in some solid research. The paper Identity Mappings in Deep Residual Networks by Kaming He and the team at Microsoft Research, a really influential one.
Definitely. So our mission, if you will, for this deep dive is to unpack how the design choices within these ResNet units really make or break the ability to train these super, super deep networks.
Yeah, we're talking networks with hundreds, maybe even thousands of layers. It's kind of mind-blowing how they made that work and get such great results on images.
It really is. And it makes you think, doesn't it? We often hear deep was better for networks, but what were the roadblocks? What stopped people before?
Well, exactly. And how can seemingly small tweaks in architecture have such a massive impact? That's really what we want to explore.
So let's start there. What was the big problem with just stacking layers higher and higher in sort of plain networks?
Well, the main hurdle, the one people kept hitting, was this thing called the vanishing gradient problem.
Ah, yes, the signal getting weaker and weaker as it goes back.
Precisely. Think of it like whispering a message down a very long line of people.
Yeah.
By the end, it's probably garbled or just gone.
Okay.
So the learning signal that travels backward during training, it just gets exponentially smaller for the earlier layers in a really deep network. They barely learn anything.
Right, rendering them kind of useless. So ResNets introduced a fix. What's the fundamental concept?
The core idea is the residual unit. Instead of forcing each layer block to learn a whole complex transformation from scratch, it focuses on learning a residual. It learns what needs to be added to the input to get the desired output.
Okay, so like learning the difference or the change rather than the whole picture.
Exactly that, like touching up a photo instead of repainting it entirely. You focus on the adjustments.
Makes sense. How does that look, mathematically? What's happening inside the unit?
So the paper lays it out. You have an input called XL. The output of the unit, XLL, is basically XLL plus this function F.
And F is the bit the network learns with the weights.
Yeah, F is the residual function, FXL, with its weights, WL. Then, the input to the next layer, XL plus 1, is some activation function F applied to that sum EL.
Okay. And the key innovation was?
The identity skip connection. In the original design, that input XL wasn't just fed into F, it was also added back after F, completely unchanged.
Yep.
So HXL was just XL.
A direct path, skipping over the main transformation block.
Exactly. And initially, the activation F, right after that addition, was ReLU.
Right, the rectified linear unit, 0 for negative, pass through for positive.
Yep. That skip connection, that identity mapping, was the first big piece. It lets the network bypass learning if it needs to.
Okay, but the paper goes deeper, right? It wasn't just about the skip connection being an identity. What about the function after the addition?
This is where they really started analyzing the signal propagation. What if both the skip connection EXL and the function F after the addition are identity mappings?
Ah, so the signal flows completely cleanly through that addition point.
Precisely. It creates this incredibly clean pathway for information, both going forward through the network and, critically, for the gradients going backward during training.
Okay, that sounds like the solution to the vanishing gradient problem. How does it work?
Well, mathematically, it cleans things up beautifully. For the forward pass, the output of a really deep layer L is just the output of an earlier layer L plus the sum of all the residuals F in between. It's additive.
No complex multiplications piling up.
Exactly. And for the backward pass, the gradient flowing back to layer L gets a component directly from the gradient at layer L. It's like an express lane for the gradient signal.
So it bypasses all the weight layers in between on that path.
On that direct additive path, yes. So even if the gradients coming through the weight layers, through the F functions, become tiny.
There's still this direct signal coming back.
Yes. That one in the equation they show ensures that the gradient doesn't just vanish. It guarantees a path. Those gray arrows in the paper's diagrams really visualize this clean highway.
Okay, that's a powerful concept. But they didn't just assume this was the only way, did they? They tested alternatives for that skip connection.
Oh yeah, they rigorously tested what happens when you mess with that identity shortcut.
Yeah.
What if it's not a pure identity?
Right. What did they try?
Well, one simple thing was scaling. Instead of X, XL, XL, they tried X lambda XL, where lambda is just a constant.
Like multiplying the shortcut signal by, say, 0.5.
Exactly. And what they found, mathematically and experimentally, is if lambda is less than 1, you reintroduce this problem where signals can shrink exponentially as they go through many layers.
Ah, because you're repeatedly multiplying by a number less than 1.
Yep. Their experiment with Lambda point 0.5 confirmed it. The error rate went up. Training suffered.
Okay, so simple scaling is bad. What else? Gating.
They looked at gating mechanisms,
Hmm?
kind of inspired by LSTMs or highway networks. These use learned gates, usually sigmoids, to control how much of the shortcut versus the residual path gets through.
More complex, more parameters.
More parameters, yes. They tried different types, like exclusive gates, but interestingly, they generally performed worse than the plain identity shortcut.
Really? Even with more flexibility.
Yeah, and they were very sensitive to initialization, especially the biases in the gates. It seems introducing those multiplicative gates just complicated the gradient flow too much.
So multiplication on the shortcut path seems to be the enemy of smooth training in deep nets,
That seems to be the takeaway. They also tried one-by-one convolutions in the shortcut.
which can be useful sometimes, right, for matching dimensions.
They can be, especially in shallower networks or for changing channel depths. But in their very deep ResNet 110, putting a one-by-one conv there actually hurt performance compared to the identity. Even a simple linear projection seemed to disrupt things.
Wow. And dropout, surely dropout on the shortcut would be bad too.
Terrible. They tried applying dropout directly to the identity shortcut's output. The network just failed to train properly.
Because dropout messes with the signal magnitude statistically.
Exactly. It's another form of disruption to that clean path. So the conclusion was pretty clear. Keep the shortcut clean. Identity is best. Multiplicative operations. Bad news for deep training.
Okay, point taken. Keep the shortcut pristine. But what about the other potential identity mapping the function Imera after the addition? The original had ReLU there.
Right. That was the next frontier. They thought, okay, the identity shortcut is crucial. What if we could also make the function after the addition an identity?
How would you do that? You still need nonlinearity somewhere, right?
You do. So they experimented by rearranging where the activation functions. Batch norm and ReLU were placed within the residual unit. The goal was to have the signal pass through the addition point without an immediate nonlinearity or normalization applied to the sum itself.
Okay, what happens if you put batch norm after the addition?
That didn't work well. Performance dropped. The reasoning was that BN normalizes the combined signal, shortcut plus residual, and this normalization actually alters the signal propagating through the shortcut path.
Ah, so it interferes with that clean identity path again, even though it's after the addition.
Seems so. It also seemed to make the loss decrease slower at the start of training. Batch norm, by the way, is that technique used everywhere now to help stabilize training by normalizing layer inputs.
Right. Okay, so BN after addition is out. What about moving the ReLU, putting it before the addition?
They tried that too. The setup was like confast BN ReLU, confast BN add a ReLU, original, versus confast BN add ReLU, confast BN ReLU add.
So the ReLU acts on the residual before it's added to the shortcut.
Yes. But this also caused problems. Because ReLU outputs only non-negative values, the residual function f could now only be non-negative.
Which limits what the network can learn. A residual should be able to increase or decrease the signal, right?
Exactly. The authors argued it damages the representational capacity. And again, performance dropped compared to the original.
So the original ordering seemed pretty good, but they still wanted that identity after the addition. How did they achieve it?
This led to their key proposal: pre-activation.
Pre-activation. Okay, what's that?
Instead of the standard conv BN ReU block, they moved the BN and ReLU before the convolution. So for one block, the order becomes BN ReLU conv.
Before the weights. How does that out?
Okay, think about the signal flow between blocks. If you have BN might ReLU conv, might ReLU conv, and then the addition, the signal coming out of the addition and going into the next block's BN hasn't been hit by a ReLU immediately after the sum.
Ah, I see. So the path between the addition in one unit and the start of the weight layers in the next unit becomes an identity path.
Effectively, yes. They call this full pre-activation when both BN and ReLU come first. It creates this sort of asymmetric application where the activation happens before the weighted effects.
And did this work? Did it help training?
Massively. This was the breakthrough. With full pre-activation, they found training became much, much easier, especially for the really deep networks.
Like that 1001 layer monster.
Exactly. The training curves they show are dramatic. The pre-activation version converges much faster and reaches a lower training error. It really supported their theory about needing that identity mapping after the addition for smooth signal propagation.
And it wasn't just faster training, right? Did it generalize better, improve the final accuracy?
Yes, there was a regularization benefit too. Having batch norm right before the weight layers seems to help control the inputs to those layers in a beneficial way.
How so?
Well, they observed that pre-activation networks sometimes ended up with slightly higher training loss compared to the original at the very end, but achieved lower test error.
Interesting. So, better generalization to unseen data.
Exactly. BN as preprocessing for the weights seems to act as a slight regularizer.
And the results they got with this pre-activation were state of the art at the time.
Pretty much, yeah. Especially on datasets like CFAR 10 and CFAR 100. They got that 1001 layer network down to just 4.62% error on CFAR 10.
Which was huge. And that was without a lot of the extra tricks people often used.
Right? Relatively standard data augmentation. They showed strong results on CFAR 100 too.
What about ImageNet, the big one?
They tested a 200-layer ResNet with pre-activation on ImageNet. It actually outperformed their original 200-layer ResNet from the first paper.
Wow.
And it was very competitive with uh, other contemporary state-of-the-art models like Google's Inception v3. They noted the original deeper ResNets showed signs of overfitting on ImageNet, and pre-activation seemed to mitigate that.
So, better optimization and better generalization from this pre-activation structure.
That's the conclusion.
One last thing going this deep, 1,000 layers. What about the compute cost? Does it become impractical?
It's definitely computationally intensive, no doubt. But the paper mentions the complexity scales pretty much linearly with depth.
Okay, so double the layers, roughly double the compute. Manageable if you have the hardware.
Right. It's not like some exponential blowup. They trained these on multi-GPU setups, which was becoming standard practice anyway.
Okay, let's try and wrap this up then. What are the absolute key takeaways from digging into this paper?
I think the big one is just how critical those identity mappings are. Both the skip connection itself being an
For
identity
direct Oracle addition.
and having an effectively identity mapping after the addition, which they achieved with pre-activation.
Hmm.
These two things together are what really enabled training those incredibly deep networks successfully.
And it shows how subtle design choices, like where you put your BN and ReLU, can have massive consequences for deep learning models.
Absolutely. It's not just about stacking layers. It's about designing the flow of information and gradients through those layers. That clean, additive signal propagation is paramount.
So the aha moment is really understanding why ResNets work so well. It's about maintaining these unimpeded information highways through the network depth.
Precisely. It unlocked the potential for extreme depth and led to huge leaps in accuracy for tasks like image recognition. It provides a much deeper intuition about signal propagation.
So for you, listening in and wanting to get the essence quickly, this research is fundamental. It shows how clever architecture, not just brute force depth, drives progress.
Yeah, it's a masterclass in analyzing and improving network design based on understanding the underlying dynamics.
It leaves you with a thought, doesn't it?
Hmm.
If these principles of direct information flow and careful component placement are so vital in neural networks,
Uh-huh.
where else might they apply? How do these ideas translate to other complex systems, maybe even outside of AI? And looking forward, what does this tell us about designing the next generation of architectures?
That's a great question to ponder. What other skip connections or pre-activations are waiting to be discovered in AI or elsewhere? Food for thought.
Definitely. Well, thanks for joining us on this deep dive into ResNet identities. We'll catch you next time.